Hey everybody, I want to use this video to talk to you about how to combine normal distributions, or more accurately, how to find the distribution of the difference of two distributions. And that might seem a little esoteric, but it will explain how we're going to do our hypothesis testing for more than one sample. Right, so that's a thing we want to do. So let's go to the notes. All right, so here's the idea. What we're going to eventually be doing is we're going to want to be comparing two samples to each other. Up until now, all our hypothesis tests have been one sample versus a number, right? But that's not always what you want to do. In fact, I would argue that's not even usually what you want to do. Usually in a real world question, you're trying to answer something. You're trying to answer, well, a comparison, right, between two different things. So for instance, do men or women make more money, right? And then so you're going to have this distribution of the money that women make and the distribution of money that men make, and you're going to want to compare the two of them to see if they are equal or not. Now, it's been pretty well established that men on average make more money than women do, but certainly that's not true, universally true, right? There are plenty of women who make more money than me, and vice versa. So so yeah, so that's usually what you want to do. Is you want to, well, often what you want to do is compare two samples to each other, which is not a thing we know how to do yet, which is of course what we're going to do in chapter 10. So I want to start off by explaining the basis for how the formulas are going to work, because this is a bit of a complication, right? In each sample, you have variance, right? So each sample is, you're not comparing like how far away is this sample from some hypothesized number where you can just subtract. It's how far away is this sample, or is like the average of this sample from the average of this other sample, and how do we account for the fact that both of them vary depending on the sample we took. So where that comes in is this. We're going to use this idea of combining normal distributions. I should really call this subtracting normal distributions, I guess, finding the difference between the distributions. Where here's the idea. So we need to know one thing that I'm not going to justify. I'm just going to let you kind of think about it, which is that if you take normal distribution, I'm going to call normal distribution A and normal distribution B, right? You have two normally distributed random variables A and B, and I take like one element in A, and I subtract from that one element in B, and that difference is now a number that I'm going to write down, I guess, right? And then I take that same element of A and I do a different element of B, and I repeat until I have taken that one thing in A, that one number in distribution A, and subtracted everything from, or subtracting everything in B from that and written down all the differences. And then you do that, you pick another element of A and you do the exact same thing. And you pick another element of A and you do the exact same thing. And you repeat until all the elements of A are gone. So in other words, you've taken all the differences of everything in A minus everything in B. So there's a lot more, just to be clear, there's a lot more things in this number of differences than there are in either distribution individually, because you're combining all the things in A with all the things in B. So there's this huge number of them. In fact, it's the number of things in A times the number of things in B. That's how many are in this set of differences. And when you do that, the thing that you get is another normal distribution. So in other words, the differences, the set of all possible differences of elements in A minus elements in B, if A and B are both normally distributed, that set of differences is itself normally distributed. And I'll let you think about why that's the case. I'll sketch a picture and we'll talk about it a little bit, but I'm not going to like mathematically justify it. One thing I do want to point out is that the standard deviation of the distribution of differences is this. It is not the difference of the standard deviations, which would be smaller. It is the sum of the standard deviations, which I'll explain. So let me draw a couple pictures here. Let's go to the whiteboard and say that I've got I've got my x-axis here, and then I have two distributions, right? I've got distribution A here, right? That goes forever right and left, and I got distribution B here. Right, I'm deliberately trying to draw this like a little bit lower and fatter just to demonstrate that they don't have to have the same mean or the same standard deviation or anything like that. So here we've got this. There's the mu sub A. And we've got mu sub B as well over here. Mu sub B. Ignore that extra mark there. Sorry, take a second to erase it. There we go. There we go. That's what we're doing. All right. So here's the idea. In each case, I'm going to do some red element, something in the red distribution over here. One of these infinite number of dots, and I'm going to subtract from it one of the blue dots. When I say subtract a dot, what I really mean is the x value of the dots. So the most common element or in A is at the mean, right? Because it's normally distributed, so the peak is right in the middle. And same thing is true for B. So the most common difference that you're going to get is also going to be the mean minus the mean, or the mean of A minus the mean of B. So that's where you see the peak of the differences. Let's do this. So I've got this down here. Now, I don't want to mislead you and think to make you think that like, oh, the difference when you subtract these two, you get something right in the middle. No, not at all. What you get is, so I have no idea where mu A and mu B are. Maybe this is 1,000 and this is 1,010, right? And then the average difference is going to be 10. It's going to be far, far to the left. Or it could be that this is negative 100 and this is 52, right? And then the difference is, the average difference is 152, which would be way to the right. So don't think that this thing that I've drawn down here and this one up here are on the same scale. But when I subtract, the most common entry is going to be mu A minus mu B, right? So whatever that value is going to be the center of my new distribution. And so the way you want to think about this is, or one thing you want to think about is, you can get like something over here that's to the left of the mean of A minus something over here that's to the right of the mean of B, and then you get this really big negative value because, right, so this is small and that's big, and it's much farther away from the mean of mu A minus mu B than, for instance, just this red dot is away from the mean of mu A. So what ends up happening is, because there are these differences in A minus B that are bigger than anything in A or in B, you get this extra large spread. So something is, so the set of all the differences is more spread out than either of the distributions individually. So what you get is this shorter kind of more spread out normal distribution that's not as high at the peak. Yeah, so basically, so the standard deviations don't exactly add together. It's actually the variances that add together. The variance of A plus the variance of B is the variance of the new set of A minus B, or A plus B if you're adding instead of subtracting, which we're not going to be doing. So this guy is mu A minus mu B, which the way I've drawn this with B being to the right of A, this number is negative here. I hope that's clear. So what you get is this normal distribution whose center, whose most common value is the difference between the means of the individual distributions, and whose standard deviation is greater than either one, because you get some of these things where the values are really big, where you're doing, mu A minus mu B, and you've got something in A that's way over here and something in B that's way over here, and so you get this huge difference. Or sometimes you do like mu A minus mu B here, and the difference is tiny, right? So you get these really small and really big differences. Sometimes it goes the other way too, where you get like a really positive number where, you know, you get something in A here and something in B here, even though the mean of B is bigger than the mean of A, there's some elements in A that are bigger than some elements in B. So you get this, difference that goes the other direction. So basically, when you subtract these two, what ends up happening is, or subtract these two normal distributions, what ends up happening is that the mean of the distribution of differences is at the difference of the means, and the standard deviation of the distribution of differences is the square root of the sum of the variances of the old distributions. So let's see what the formula for that looks like. I actually pointed it out earlier, I think, right here, right? So if A and B are both normal distributions, then the distribution of all the differences of elements in A minus elements in B is approximately normal, with a mean of this, mu A minus mu B, right? So the mean is the difference, the mean of the differences is the difference of the means, and a standard deviation of this. So you might have been wondering way back when we introduced the idea of standard deviation, I talked about variance and said we were going to use it a little bit later, and actually I referenced this particular lecture, although I do not expect that you remembered that. For this reason, variance has this nice property that if you combine normal distributions like this, either by adding or subtracting them or doing other things to them, you can add the variances together to get the variance of the new thing. Consequently, this right here is the variance of A minus B. So the standard deviation of A minus B is the square root of that, right here. So this is how you get the distribution of all possible differences of two normal distributions. So here's what we're going to do with that. Let me kind of introduce that in a gentle way. Gradually is the word I'm looking for. So I got two populations. Population A is this distribution. It's a normal distribution with a mean of 17.3 and a standard deviation of 3.5. B is this distribution. It's the normal distribution with a mean of 6.8 and a standard deviation of 4.1. I'm not going to set this up in any way. These are just two random distributions. And I want to find the distribution of all possible differences, right? The all possible differences of everything in A minus everything in B. And so I'm just going to use the formula, right? I'm just going to do this right here. Let's flip to the calculator and do that real quick. So I have my new mean. Just turn this on. So my new mean is going to be 17.3 minus 6.8. All right, so there's my new mean, and my new standard deviation is the square root of 3.5 squared plus 4.1 squared, which you will notice is bigger than either one of them individually, as it would have to be. All right, so there we go. My new distribution has a mean of 10.5, there's a normal distribution, I should say, with a mean of 10.5 and a standard deviation of 5.39. That's it. That's how you use that's what all that explanation is for. So now, let's see what we're gonna do with that information. So here we have a sample of size n sub a equals 25. And notice I'm using the subscript to identify which distribution I'm drawing it from, right? So I'm taking a sample of size 25 from population A, so I'm calling it n sub a. And a sample of size 36 from population B, so we're calling it n sub B. So the central limit theorem tells us what the sampling distributions of x bar sub A and x bar sub B are, right? It's just, so A and B are both normally distributed, so I don't have to worry about the fact that this is only size 25. This one was already big enough anyway. So what I've got is that my x bar sub A has a mean of 17.3 and a standard deviation of 3.5 over the square root of 25. And x bar sub B has a mean of 6.8 and a standard deviation of 4.1 over the square root of 36. Right, so let's find out what those things would be. So I've obviously chosen 25 and 36 to be easy here. So we've got 3.5 divided by square root of 25, there's 5. 0.7, obviously, and then 4.1 divided by the square root of 36 gives me that. And so those are the standard deviations, the sampling distributions, x bar A and x bar B. And then the means are the same. Means are 17.3 and 6.8. All right, so now I've got this distribution, x bar a minus b. So it is the sampling distribution of all the differences in averages between something in A and something in B, right? So the standard, the sampling distribution x bar sub A is itself a normal distribution, as is x bar sub B. So now what I want is x bar A minus x bar B, which is probably how I should have written that here. Sorry, I think my notation is a little confusing. I should have called this x bar sub A minus x bar sub B to correspond with the same notation I was using up here, A minus B. Where x bar sub A minus B is the distribution of all possible differences between x bar A and x bar B. And notice that the sample size is different for these two distributions, but that makes no difference at all, right? That doesn't matter at all because x bar sub A is a normal distribution, x bar sub B is a normal distribution. This works for any normal distributions. So there you go. We can just subtract those two. So we're gonna do the exact same thing, right? I'm just gonna do this formula, mu A minus mu B, and then this formula, square root of sigma sub x bar A squared plus sigma sub x bar B squared. Right, now I found those on my calculator over here. Right, there's x bar sub A, there's x bar sub B, and we're going to square those in and add them up. So a thing you can do on your calculator if you want to get some extra decimal precision is something like this. I can do this number squared. Now, of course, I could have just typed in 0.7 squared. I just wanted to show you could do it. Plus this squared, right? You don't have to retype them. I'm just scrolling up and hitting enter on the appropriate number that I want. So I get 0.978, we'll say. So 0.978 is the standard deviation of the sampling distribution of all the possible differences between x bar A and x bar B. Or I should say not the sampling distribution, the distribution of all the possible differences between x bar A and x bar B. That's really what I wanted to say there. Nope, that's not the right share. Sorry, my bad. There's the one I wanted. And so that is my answer to number 3. Or the mean is the same. The mean is the 10.5, right? It's still 17.3 minus 6.8. It's the standard deviations that are interesting. All right, that is enough random theorizing. Let's do an actual problem. All right, so I've got American men's heights are normally distributed with a mean of this many inches and a standard deviation of 2.9 inches. So American men's heights are approximately normally distributed with a mean of 69.5 and a standard deviation of 2.9. I'm going to call that distribution M for men, obviously. American women's heights are normally distributed with this mean and that standard deviation. So W, the distribution of all women's heights, all American women's heights, is approximately this. So I want to find the distribution of M minus W. And then let's talk about what this is first. So M is all the men in the United States. It's the distribution of their heights. W is the distribution of all the women's heights in the United States. M minus W is the distribution of the differences in heights between men and women. So it's if I took all the men in the United States and stuck them in one room, and all the women in the United States and stuck them in another room, grabbed one man at random and one woman at random, took their and then subtracted their heights, like how did M minus W, so the man's height minus the woman's height, wrote that number down, and then repeated that until I had done every single possible combination. That is what M minus W is the distribution of. So let's find it. So I'm going to do exactly the same thing we did before. We're going to do 69.5 minus 64.3 for the mean, and then the standard deviation is going to be the square root of 2.9 squared plus 2.4 squared. So let's go type that into the calculator. So square root of 2.9 squared plus 2.4 squared. Whoops. Let's just clear that out. So 2.9, I don't know why. 2.4 squared. I'll have to go back and look at the video to see where that extra space came from. Now we get this, 3.764. That's the standard deviation of the distribution of all possible differences between men's heights and women's heights. And the mean is this, 69.5 minus 64.3. Right, so the mean is 5.2. So I'm going to go ahead and write that down and draw a picture of it because we're going to be using it in just a second. So mean of 5.2, standard deviation 3.76. Nope. So we have, I don't want fuchsia, black here. So we're going to have mean of 5.2. So this inches, of course. Let's move that out of the way. So this is N 5.2, 3.76. Right? And so that is the distribution of all possible differences in heights between a man and a woman, American man and an American woman. That's the distribution. All right, let's see what we're going to do with this distribution. What is the probability that if you select one random American man and one random American woman, the man is at least 6 inches taller than the woman? All right, so the way you want to think about that is if I take a random man, I call his height little m, and I take a random woman and I call her height little w, if I do m minus w, what's the probability that's at least 6? Well, this thing that I just drew is all the possible differences. This is all the m minus w's. So the probability of having m minus w be at least 6 is this area over here, right? Where this is 6, and so this says that m minus w is, nope, that's the wrong way. More than 6 is this area. So if I want to find that, I just do normal CDF, of course, right? Normal CDF of 6 to infinity with a mean of 5.2 and a standard deviation of 3.76 will give me what I want. So let's do that. So we're going to do, whoop, go back here, second bars, normal CDF of 6 up to infinity, so it's a large number, with a mean of 5.2 and a standard deviation of 3.76. And there we go. It is 41.6% likely that the man will be at least 6 inches taller than the woman, which I hope that seems at least generally plausible to you, right? This is a little bit bigger than the average difference, so you'd want a man who's a little taller than average or a woman who's a little bit shorter than average or both. And so for both those things to occur, it's not super likely, but it's not super unlikely either, right? So 41.6%. All right, what's the probability that the woman is taller than the man? Well, let's go see where that shows up on our distribution. So if I'm saying that the woman is taller than the man, that means that when I do m minus w, right, this is the distribution of all the m minus w's, which by the way, we could have done this as w minus m just as easily. This number would be negative, but this number would be negative. That's the only difference. It would be essentially takes the distribution and flips it over. So I wanted to find where the woman is taller than the man. Well, they would be equal heights when m minus w is 0, right? So here's 0 over here. And all the area to the right of 0, m minus w is positive. That is to say the man is taller. And all the area to the left of 0, where it's negative, is where the woman is taller. So I'm looking to find this area over here to answer where the woman is taller than the man, right? It's going to happen some of the time, not super often, but some of the time. And so now I'm looking for minus infinity up to 0 in this distribution. So let's normal CDF that guy. Computer, there we go. So we're going to do normal CDF negative infinity, so negative something big up to 0 with same distribution, and I get that about 8.3% of the time, which I hope sounds plausible, right? If I take a random woman and a random man, occasionally the woman will be taller than the man, a little bit less than 10% of the time, which that seems reasonable. Yeah, so that's my answer. About 8.3% of the time, the woman is taller than the man when I do this. All right, now let's get into how we're actually going to use this, which is I got X bar M and X bar W. So the sampling distribution of the sample mean of 10 men and the sampling distribution of the sample mean of 10 women. And I can use the central limit theorem here because the population distributions are normal. So even though these numbers are smaller than 30, that's fine because the population distributions themselves are normal. So central limit theorem applies just fine. And so now I want to find the distribution of X bar M minus W. So in other words, if I take 10 men's heights, I grab 10 men out of that first room that has all the men and average them or average their height. And I take 10 women out of that room that has all the women and average their height and then subtract the averages. So the difference of the averages, this thing that I'm finding right now is going to be the distribution of all those differences. So we're going to have, as before, the same averages, right? So each of X bar M and X bar W are going to have the same averages, but their standard deviations are going to be divided by the square root of 10. So 2.9 over root 10 and 2.4 over root 10. So we should find those things. Let's do that. Calculator. So we've got 2.9 divided by the square root of 10. And same thing, 2.4 divided by the square root of 10. So X bar M has a mean of 69.5 and a standard deviation of 0.917. And X bar W has a mean of 64.3 and a standard deviation of 0.759. Okay, so I found X bar M and X bar W then, and of course they're still normal. And part E asks to find the distribution of all the differences between those. So I'm going to do the means, again, 69.5 minus 64.3, still 5.2. The standard deviation of the distribution of differences of average heights of 10 men and average heights of 10 women is going to be this. It's going to be the square root of that squared plus that squared. Just like it was before, so 1.19. So let's go back over here. So this right here, the distribution of differences between the sampling distribution of average height of 10 men and the sampling distribution of the average height of 10 women is 5.2 is a normal distribution with a mean of 5.2 and a standard deviation of that thing that we just found, which was 1.19. Right, so let's go write that down on a whiteboard here. So this guy is X bar M minus W is N 5.2 1.19. That's a terrible 9. Right, so we're going to graph that. Of course, it just looks like every other normal distribution when I'm sketching it. 5.2, standard deviation of 1.19. And then within that, now we're going to actually answer a question now that we found a sampling distribution here. I want to find the probability that in a sample of 10 American men and 10 American women, the average height of the men is at least 6 inches greater than the average height of the women. Well, we're going to do that exactly the same way we did the previous one, which is just shade, right? So if for the average height of the men to be at least 6 inches greater than the average height of the women, that means that we are looking over here. Right, so very similar to what we did before, it's just got a different standard deviation. This is going to be a smaller percentage. So let me explain how I can know that without doing any math. This is an area that is away from the mean, and the standard deviation got smaller. So that means that this distribution, despite what it looks like, is significantly less clustered around the mean than this distribution, right? This distribution has standard deviation of 3.76, and this distribution has a standard deviation of 1.19, which is about a third of the size of the other one. So this one is much smaller. That means that it is more tightly clustered around the mean. And so that means that this area here that's in the tail away from the mean is smaller. So let's find out what that number is. So we're going to share up the calculator here, and we're going to normal CDF of, it was 6 to infinity, with a mean of 5.2 and a standard deviation of 1.19. And you can see it's smaller, 25% of the time. So whereas about 40% of the time, here, that one, if you took one man and one woman, you would get the man being at least 6 inches taller. If you take an average of 10 men and 10 women, average of 10 men, average of 10 women, find the difference there, the thing that you're going to get is you're only going to get that the average of the men's heights is 6 inches greater than the average of the women's heights or more, only about 25% of the time. So this decrease in probability is basically what we're going to use to our advantage to compare sample of one type and a sample of another type to see which one is bigger, right? By taking a larger sample, we were able to get more information and therefore decrease the likelihood of something being far away from the mean. Of course, that's what we're going to do to when we're doing a hypothesis test. So let's look at how we're going to compare these two population means, and then I will go ahead and end this video, and we'll start doing specific examples in the next one. So here's the basic idea. We're going to do a hypothesis test. We're going to be asking questions about whether the mean of one population is greater than the mean of another population, right? And so if we were asking about, like, is the mean of men's heights greater than the mean of women's heights? I mean, that's not a real question we would ask, but that is a question of the type that we could ask. We're going to end up getting, to do a test like that, we're going to want to do one of these three things. And by the way, we're not going to ask, is it true that this population has a mean that is at least, say, 6 units greater than this other population? We're just going to ask the question of, is this one bigger than that one, right? Which is, that's the sort of question you usually want to ask. We can do a little bit more with it, but we're not going to. We're just going to do these. A thing I want to point out is that for each of these, the null hypothesis is 0, right? The numbers associated with the null and alternative hypothesis here are always 0, because if mu1 is smaller than mu2, that's another way of saying that mu1 minus mu2 is less than 0. If mu1 is bigger than mu2, then mu1 minus mu2 is bigger than 0. And if we're just checking to see if mu1 and mu2 are equal, then mu1 minus mu2 is not equal to 0, right? Either direction causes us to think that they're not equal. We're going to take advantage of that, by the way. We're going to use this, the fact that, I can't highlight part of this, but we're going to use the fact that mu1 minus mu2 equals 0 in all of our null hypotheses, because remember, when we're doing on hypothesis tests, sorry, I bit my tongue there, we always start by assuming the null hypothesis is true, and if the null hypothesis is true that mu1 minus mu2 equals 0, well, there's some neat stuff we can do with that, and we're going to do a very little bit of it. So with that, I'm going to go ahead and stop talking, I think, and end this video, and then for the next video, I'm going to explain how we actually do a test. Right, we're gonna do a t-test here. I'll probably run through this test here. And then we'll do a test, and then we'll do the sort of test we actually do, which is t-tests, and then later in the third video we'll do proportions tests, and then in the fourth video we will do paired tests, which turn out to be the nicest and most useful of them, I think. So anyway, all right, I'm going to go ahead and end the video here. Stop sharing, and I will go ahead and see you guys in the next one.